Imagine this, you're cruising at 30,000 feet, sipping lukewarm coffee, when suddenly, silence. The engines? Gone. Poof. Vanished. Sounds like an absolute nightmare, right? The kind of scenario ripped straight from a Hollywood disaster flick. But what if I told you that in some of the most heart-stopping aviation emergencies, losing all power isn't necessarily a death sentence? What hidden physics and incredible engineering turn an uncontrollable plummet into an impossible, breathtaking glide? Get ready, because we're about to dive deep into the mind-blowing science that lets planes cheat death. The first twist? Aerodynamics. Even without thrust, a plane is a giant wing. It uses the very air pushing against it to generate lift. Pilots aren't just falling, they're gliding. Every aircraft has a glide ratio. For every foot it drops, it travels a certain distance forward. A Boeing 747, even with dead engines, can glide for incredible distances. That's why pilots immediately angle the nose down, to maintain airspeed, keep air flowing over the wings, and turn a brick into a very heavy, very fast, very efficient glider. It's a race against gravity, but one with a surprising amount of control. But wait, what about steering? Most planes rely on hydraulic systems for flight controls, flaps, rudder, elevators. Lose engines, lose power, lose hydraulics, right? Wrong. This is where engineering redundancy kicks in. Modern aircraft often have multiple, independent hydraulic systems, powered by different engines. If one fails, another takes over. And if all engines fail, many planes have an auxiliary power unit, a small jet engine in the tail, to generate electricity and power key systems. Still no go? Then the ram air turbine, or RAT, deploys, using airflow to spin a small propeller and provide emergency power. It's like a tiny windmill saving the day. Speaking of miracles, let's talk about Air Canada Flight 143, famously known as the Gimli glider. Mid-flight, at 41,000 feet, this Boeing 767 ran out of fuel. Both engines dead. Why? A mind-boggling mix-up between metric and imperial fuel calculations. The plane became a 132-ton glider. But here's the twist: the pilot, a former glider pilot, used his unique expertise to navigate a dead plane to a disused airfield. They even executed a daring slip maneuver to lose altitude quickly without gaining too much speed. This wasn't just luck, it was physics, engineering, and sheer pilot genius combining for an impossible landing. What about when the plane itself starts to break apart? Think Aloha Airlines Flight 243. Mid-flight, a huge section of the fuselage tore away, exposing passengers to the sky. It was a terrifying, almost impossible scenario. But here's the science: planes are designed with fail-safe structures. Even with a massive hole, the remaining structure distributed the stress, preventing total disintegration. The aircraft's aluminum skin is designed to be tough, but also to flex and deform under pressure, not shatter. Plus, the cabin pressurization systems, though compromised, helped manage the sudden pressure change, saving lives. It was an extreme test of structural integrity, and the engineering barely held. At the heart of every impossible recovery is a human element, the pilot. No amount of engineering can fully replace quick thinking and ice-cold nerves under unimaginable pressure. Pilots train for years for these black swan events. They don't just fly, they troubleshoot, adapt, and make life-or-death decisions in seconds. The physics of flight, the mechanics of the aircraft, they are tools. The pilot is the master craftsman. Their ability to quickly assess a failing system, understand its implications, and apply unconventional solutions is a true superpower. It's the ultimate fusion of man and machine against impossible odds. And then, of course, there's the miracle on the Hudson. U.S. Airways Flight 1549, dual-engine failure just after takeoff, thanks to a massive bird strike. Captain Sully Sullenberger had mere minutes to decide. Land at an airport? Impossible. The only option? The Hudson River. This wasn't just a crash, it was a controlled ditching. The plane's design, reinforced for impact, held together. The emergency slides inflated, doubling as life rafts. And crucially, every single passenger and crew member survived. It was the perfect storm of physics, pilot skill, and rapid emergency response, proving that even a plane in the water isn't necessarily game over. The survival story doesn't end with the landing. Once the plane is down, whether on a runway, a field, or water, the last line of defense kicks in. We're talking emergency exits, lighting, and rapid evacuation protocols. Ever notice those floor-level lights? They're there to guide you through smoke. Survival rafts and vests for water landings? Standard. Even the materials inside the cabin are designed to be fire-resistant. This isn't just about surviving the impossible flight, it's about surviving the impossible aftermath. Every component, from the seatbelt buckle to the escape slide, has been engineered for your survival. So, the next time you're soaring through the clouds, remember, there's more than just magic keeping you up there. It's a symphony of brilliant physics, redundant engineering, and human ingenuity. From the invisible forces of lift and drag to backup hydraulic lines, emergency power units, and the incredible training of pilots, every single element works together to turn terrifying emergencies into astonishing tales of survival. It's a testament to how far we've pushed the boundaries of flight, constantly learning from failures to build safer, more resilient machines. Aviation disasters are harrowing, but the stories of impossible recovery are pure human triumph.